Beneath the endless canopy of stars, human thought flickers like a fragile flame in a boundless night. The universe stretches beyond imagination. Galaxies adrift in oceans of darkness, constellations that outlive civilizations, and light that has traveled for billions of years to meet the eye. Against this immensity, the mind dares to ask, what is reality itself? Perhaps existence is not as solid as it seems. Perhaps it is a veil, delicate and shimmering, thinner than glass, trembling like light upon water. The cosmos, with all its planets, its storms of fire, its rivers of stars, may be no more than a surface, a shadow play upon an invisible stage. What if every detail, from the birth of galaxies to the beating of a human heart, is written not in 3 dimensions, but in 2? What if the vast theatre of existence is only a projection, cast outward from a boundary that no eye can see? Physicists whisper of a strange possibility, one that unsettles the very meaning of being. That time, memory and matter itself could be illusions, echoes of information etched on the edges of reality. The world may be nothing more than a hologram, a universe of shadows and light, suspended on a surface far beyond reach, and so the question lingers, haunting and profound. Could everything we know, every star, every thought, every dream, be nothing more than the image of a deeper truth, a universe that is, at its most fundamental level, only 2-dimensional? The early years of the 20th century brought with them a quiet revolution. For centuries, space had been imagined as a stage, fixed and eternal, upon which the motions of matter played out. Isaac Newton had written of it as an absolute arena, unaffected by the drama it contained. But with the dawn of Albert Einstein's relativity, that stage itself was revealed to be a live spacetime, the union of geometry and duration, bent under the weight of stars and planets. Light itself curved along its surface, not because of invisible forces, but because space was not what it seemed. It was malleable, fluid, capable of stretching and folding like a fabric. What had once been thought of as emptiness became a dynamic player in the universe's unfolding story. The implications unsettled the very foundation of physics. Reality could no longer be understood as rigid and independent. Instead, geometry and matter were fused in an endless dialogue. The mass of the sun told space how to curve, and the curvature of space told planets how to move. The cosmos had become a tapestry, and every thread was woven into another. Yet even in this new vision, one truth remained assumed. The universe was still thought to be 3-dimensional in its spatial form, with time flowing alongside a cathedral of depth and extension. Vast in its corridors, unfathomable in its halls, decades later, a different kind of revelation would begin to stir. It came not from the stars, but from the subtleties of light itself. In 1947, Hungarian scientist Denis Gabor sought to improve the resolution of electron microscopes. His experiments led him to an idea that seemed like alchemy, the ability to record and later reconstruct a 3-dimensional image using only 2-dimensional data. He had invented the hologram in its first fragile form. The hologram was simple: interference patterns of light, frozen upon a photographic plate. Yet when illuminated, those patterns unfolded into depth, producing the illusion of 3 dimensions from a flat surface. At the time, it was a tool of optics and engineering, a method to sharpen the human eye upon the microscopic. But in its shimmering mathematics, it carried an idea far more profound, that surfaces could contain volumes, that depth might be nothing more than a trick of encoded light. The parallel between Gabor's holograms and the universe itself would not be drawn immediately. For now, the hologram was a marvel of technology, not of philosophy. But whispers had begun. Whispers that the solidness of depth could be deceiving. By the 1970s, the frontier of physics had shifted once more. The cosmos, once defined by relativity and the curvature of space, now bent toward the enigma of black holes. These dark horizons, predicted by Einstein's equations and confirmed by astronomical observation, were no ordinary objects. They were places where geometry reached its breaking point, where space fell inward upon itself and time slowed to a halt. At their center, singularities defied description, compressing mass into realms beyond measure. Was Jacob Bekenstein, a young Israeli physicist who first dared to ask what black holes meant for the laws of thermodynamics. Every object in the universe, he argued, carries entropy, a measure of information, of disorder, of the microscopic states hidden beneath its surface. But what of black holes, which devoured matter without trace? If they were to obey the same laws, they must possess entropy as well. And if they had entropy, then information about what fell into them could not simply vanish. Bekenstein proposed a radical measure. The entropy of a black hole was not proportional to its volume, as one might expect, but to the area of its event horizon, the two-dimensional boundary that separated inside from out. This was the first whisper of a flattening universe, a suggestion that the information describing matter was written upon a surface, not within a depth. Stephen Hawking, skeptical at first, would soon provide a discovery that deepened the mystery. In 1974, he revealed that black holes were not silent quantum effects at their horizons caused them to emit radiation, a faint glow now known as Hawking radiation. Given enough time, a black hole could evaporate, dissolving back into the cosmos. But if it did so, what of the information swallowed within? Was it lost forever, breaking the sacred laws of physics, or did it linger upon the horizon, etched like hieroglyphs in the geometry of space? Together, Bekenstein and Hawking had pointed toward a new truth, that the universe might not keep its secrets buried in depths, but inscribe them upon surfaces. The three-dimensional volume within the black hole seemed less important than the two-dimensional boundary that defined it. The horizon became a ledger of reality, a sheet of information that suggested the cosmos itself could be holographic. These ideas unsettled physics in ways that could not yet be grasped. They implied that the universe might be flatter than imagined, that its deepest reality was written, not in the depths of space, but upon its edges. For the first time, the notion that everything could be projected from a more fundamental surface entered the scientific imagination. It was only a whisper then, faint, and almost impossible to believe. Relativity had taught that space could bend. Holography and optics had shown that depth could be conjured from surfaces, and black holes had revealed that information clings not to volume, but to horizons. Pieces of a puzzle were beginning to emerge, scattered across decades and disciplines. Pieces that would one day assemble into a vision so radical it would redefine the meaning of dimension itself. The first whispers of flatness had been heard, and the universe, once thought to be an infinite cathedral of depth, had begun to tremble with the possibility that its walls were thinner than imagined. In the deep vaults of space, where light itself surrenders and time bends towards silence, black holes stand as monuments to the unknown. For decades after Einstein's equations first foretold their existence, they remained little more than mathematical curiosities, too strange to be real, too monstrous to belong to the fabric of nature. Yet the cosmos revealed them nonetheless. Collapsed stars whose gravity had no end, regions where escape was impossible, where the very geometry of spacetime folded in upon itself. These objects were thought to be perfectly black, swallowing everything without reply. No signal could escape their pull. No whisper could cross the horizon that marked the boundary between the world we know and the abyss beyond. For years, the black hole was imagined as the perfect tomb, eternal, mute, unchanging. Then came a revelation that shook physics to its core. In 1974, Stephen Hawking, working at the intersection of quantum theory and general relativity, uncovered something unexpected. Black holes were not entirely silent. Instead, they glowed from the turbulent interplay of quantum fields at the very edge of the event horizon. Particles flickered into existence. Pairs of virtual particles, forever dancing in the vacuum, found themselves caught in the extreme geometry of a black hole. One would fall inward, the other outward, and the outward particle would escape as radiation. This faint glow, immeasurably weak yet theoretically inevitable, came to be known as Hawking radiation. What it implied was staggering. Given time longer than the age of galaxies, longer than the life of stars, a black hole would not persist forever. It would slowly evaporate, losing mass through this radiation until it vanished entirely. The great devourer would itself be consumed by its own physics, dissolving back into the vacuum from which it was born. Yet in this revelation lay a deeper wound. If a black hole could evaporate into nothing, what became of the matter it once devoured? Stars, planets, light, and dust. Everything that crossed its horizon was thought to vanish within. But if the black hole itself disappeared, would all of that information disappear too? This was not merely an academic question. At the heart of physics lies a principle older than relativity, older than quantum theory, the conservation of information. The universe, in all its transformations, does not permit the destruction of information. Particles may scatter, stars may collapse, atoms may shatter, yet the fundamental data of their state endures. It may be scrambled, hidden, diffused, but never erased. Hawking's discovery appeared to defy this law. If black holes could truly evaporate to nothing, then the information they consumed would be lost forever. It would not merely be inaccessible, it would cease to exist. Such a loss would unravel the logic of physics itself, leaving the universe with broken rules, a story with missing pages. The paradox was born. The information paradox. Across the halls of science, the implications spread like fire. To some, it was intolerable, for if information could be destroyed, then determinism itself would collapse. The present could no longer be tied to the past, and the future would drift unmoored from both. The laws of quantum mechanics, the most successful framework ever built, would fracture under their own weight to others. The paradox whispered of something more profound. Perhaps information was not lost after all. Perhaps it lingered, hidden not within the unreachable depths of the black hole, but upon its surface. The event horizon, that silent boundary where gravity and light meet in eternal tension, became the stage for this speculation. Could it be that every particle that fell in, every photon consumed, left its mark upon the horizon itself, not destroyed, not forgotten, but flattened, inscribed into the two-dimensional fabric of the boundary? It was as though the black hole were a cosmic ledger, a record keeper at the edge of oblivion. The three-dimensional chaos of matter within might dissolve into mystery, but its information, the essential blueprint of its existence, remained etched into the thin veil of surface. This suggestion, fragile yet unavoidable, transformed the image of black holes. They were no longer mere abysses. They were storytellers of the universe, keepers of memory in the language of geometry. Jacob Bekenstein had glimpsed the first hints of this years before, when he argued that black holes must possess entropy proportional to the area of their horizons, not their volume. Now Hawking's paradox breathed new urgency into the question. If entropy was surface-bound, and if evaporation threatened to erase everything, then the horizon itself must be a canvas on which the universe preserves its truth. Shock was profound. It implied that reality itself may be structured upon surfaces, that dimensions are not what they seem. The notion of depth, of volume, of the solidity of three-dimensional space began to tremble under the weight of this paradox. Perhaps what we call space is not fundamental at all. Perhaps it is an emergent mirage, born of information encoded elsewhere. For physicists, black holes became more than objects. They became laboratories of reality, experiments written not with instruments, but with mathematics and imagination. Each horizon a mystery, each equation a riddle. Stephen Hawking himself wrestled with the implications for decades at times. He suggested that information was indeed lost, that the universe must accept a wound to its laws. At other times, he yielded to the possibility that the information survived, encoded upon the horizon in ways too subtle to yet decode. He changed positions more than once, mirroring the turbulence of the scientific community as it circled around the paradox without resolution. The debate cut through the very heart of physics. Einstein's general relativity demanded one story, quantum theory demanded another, and between them stood the black hole, silent and implacable, embodying the contradiction both could not resolve. As decades passed, the paradox deepened, drawing into its orbit the greatest minds of the era. Some proposed that information escapes in subtle correlations within Hawking, radiation itself. Others argued that the black hole horizon is a hologram, projecting the illusion of depth from the data it contains. Still others ventured into the strange terrain of string theory, where the mathematics of higher dimensions offered new ways to encode what might otherwise vanish. Whatever the path, all roads pointed toward a startling possibility that the black hole was not an exception to the universe, but a window into its very nature. That what appeared as a singular object of collapse was instead a clue to the construction of all reality. That the same principle which preserved information at the horizon might also govern the universe itself. Information paradox became more than a puzzle of astrophysics. It became a mirror held up to the cosmos, reflecting a truth we had not expected to see. The universe, in all its luminous complexity, might be holographic in essence. What we perceive as depth could be projection. What we call reality could be inscription. And every star, every atom, every moment could be a surface echo of something deeper, flatter, more fundamental than sight allows. The shock of Hawking's discovery still reverberates through science today. It reminds us that black holes, those ancient enigmas of collapse, may be more than destroyers. They may be the keepers of cosmic memory, and within their paradox lies not only the fate of information, but the secret architecture of the universe itself. The paradox of black holes had opened a wound in physics, one that could not be ignored. The greatest minds of the age circled it like navigators around a whirlpool, uncertain whether it concealed destruction or revelation. At its heart lay the question of information, of whether the universe itself obeyed its own laws or betrayed them at the edge of collapse. In 1993, a bold voice rose into this silence. Gerard 't Hooft, the Dutch theoretical physicist, looked into the abyss of black hole paradoxes and proposed an idea so radical it seemed closer to poetry than to physics. He suggested that the information contained in any volume of space could be described entirely by data written upon its boundary, not the inside, but the edges, not the depths, but the surface. This was the holographic principle. It was as though the universe itself might be a book that could be read entirely from its cover. Every particle, every law, every memory of motion inside a region could be reconstructed if one knew the inscriptions upon the boundary that enclosed it. What appeared three-dimensional was, at its foundation, no more than a two-dimensional code. The echo of Dennis Gabor's hologram was unmistakable. Just as light scattered across a flat plate could conjure the illusion of depth, so too could the boundaries of spacetime hold the essence of everything within. The paradox of black holes was not a violation of physics, but a revelation of a deeper structure. Reality, it seemed, was holographic. Leonard Susskind, a physicist at Stanford, became one of the fiercest champions of this vision. He saw in 't Hooft's principle not merely a resolution to the black hole information paradox, but a blueprint for the universe itself. The event horizon of a black hole was not unique. It was a metaphor for everything. Susskind argued that all of three-dimensional space could be described by information on a two-dimensional surface, the cosmic horizon of the universe. We live, he suggested, in a projection, a grand hologram, where depth and volume are illusions of perspective. The universe was no cathedral of stone, but a mirage of light upon glass. The implications were staggering. If the holographic principle was true, then the very geometry of space and time was not fundamental. It was emergent, a phenomenon rising from information, the way temperature rises from the motion of molecules, or the way a hologram rises from patterns of interference. Space-time itself might be a consequence, not a foundation string theory, already weaving its own radical narrative, found unexpected harmony with this principle. Born from the attempt to reconcile quantum mechanics with gravity, string theory described the universe not as points and particles, but as vibrating filaments of energy, each resonance giving rise to a particle of matter or a force of nature. Its mathematics demanded more dimensions than could be seen, and in its intricate symmetries, it hinted that space and time were not what they seemed. When the holographic principle entered string theory's framework, the pieces began to align. The mathematics suggested that what we call space-time could itself emerge from lower dimensional structures, woven together by the threads of quantum entanglement. The depths of the universe might be the shadows of something flatter, simpler, more fundamental than perception allows. In 1997, a young Argentine physicist named Juan Maldacena took these whispers and transformed them into a revelation. He proposed what would become known as the ADS-CFT correspondence, a duality between two worlds that seemed, at first glance, entirely different. On one side stood anti-de Sitter space, a higher dimensional universe with negative curvature, a strange geometric setting for string theory's equations. On the other stood a conformal field theory, a lower dimensional quantum system defined without gravity. Maldacena's conjecture declared that these two descriptions, so unlike in appearance, were in fact identical. Every calculation in one could be mirrored perfectly in the other. Every event in the higher dimensional bulk was encoded on the lower dimensional boundary. It was as though two mirrors faced one another across reality, each reflecting the same truth in different forms. Space-time itself could be nothing more than a projection from quantum fields written on a surface beyond our perception. This correspondence electrified physics. It was not a vague suggestion, but a mathematically precise equivalence, a proof of concept that the holographic principle was more than metaphor. The black hole paradox had opened the wound, but Maldacena's conjecture offered the first glimpse of a cure. Within this framework, black holes became holographic objects, their entropy explained by the information encoded upon their horizons. The paradox of Hawking evaporation softened, for if the holographic duality was correct, then no information was ever lost. It was simply transformed, preserved upon the surface while the bulk illusion played out within, yet the implications reached far beyond black holes. If ADS-CFT was real, it meant that gravity itself, the curvature of space-time, the architecture of Einstein's universe, was not fundamental. It was emergent, a mirage born of quantum entanglement on a boundary. The most familiar force of all, the one that pulls tides and bends starlight, might be no more than a shadow of a deeper, flatter truth. Physicists tested the duality in every corner they could, in strongly coupled quantum systems, in the thermodynamics of black holes, in the behavior of entanglement entropy. Again and again, the mathematics held. The mirror never cracked. But the triumph was tempered by caution. Maldacena's conjecture applied to a universe with negative curvature, an anti-de Sitter space, while the cosmos humanity inhabits is flat or nearly so, expanding, with dark energy into an unknown future. And yet the principle was too elegant, too powerful, to dismiss. If such a duality could exist in one geometric setting, might it not exist in another? Could the universe itself, in all its expansion, obey a holographic law still hidden from view? For decades, this question has haunted the edges of physics. The holographic principle remains both a tool and a mystery. It allows calculations once impossible to become clear. It transforms paradoxes into symmetries, and it whispers of a universe where reality is less than it appears, where the walls of existence are thinner than imagination dares to believe. The emergence of this principle did not resolve the mystery of dimension, but it deepened it. What began as a question of black holes became a question of everything. If space-time is emergent, then what is it emerging from? If the universe is holographic, then what is the surface upon which it is written? And if 3 dimensions are illusion, then what is the true stage of reality? In the silence that followed Maldaceno's conjecture, physics found itself standing before a new abyss. Not the abyss of collapse, but the abyss of understanding. The holographic principle had emerged, shimmering like a vision on the horizon, both promise and riddle. It suggested that the universe is written twice, once on a surface and once in the depths we believe to be real. And in that doubling lies the possibility that everything humanity calls reality is only a projection, cast upon the screen of eternity by laws we cannot yet see. The oldest light in the universe still lingers, stretched thin across the heavens. It is faint, only a whisper of warmth now, but it carries the memory of everything that once was. This is the cosmic microwave background, the fossil glow of the Big Bang, a remnant from when the universe was only 380,000 years old. It is not a scattered haze, but a precise tapestry of temperature fluctuations, minute differences, only fractions of a degree, yet written across the entire sky. These patterns are the universe's first diary, etched in radiation, recording how matter clustered, how galaxies would one day form, and how space-time itself unfolded. For decades, cosmologists studied this light as a window to the past, but as the holographic principle emerged, they began to ask a new question. Could the background radiation hold evidence that reality itself is not 3-dimensional, but written upon a 2-dimensional canvas? When scientists mapped the cosmic microwave background with exquisite precision, first with COBE, then WMAP, and finally Planck, something strange appeared. The fluctuations in the data could be described with remarkable efficiency by 2-dimensional mathematical models. It was as though the ancient light was not just a fossil, but a hint pointing toward a flatter truth beneath the illusion of depth. At the Perimeter Institute and Fermilab, theorists began to push deeper. If the universe is holographic, then space-time itself must be quantized, not infinitely smooth, but pixelated, like the surface of a digital screen seen up close. Each bit of information would occupy a finite patch of area, a unit so small it could only be measured in Planck lengths, 10 to the minus 35 meters, far beyond the reach of microscopes, yet perhaps not beyond the reach of clever experiments. The search for this holographic noise became a new frontier. Physicists wondered if reality, when pushed to its limits, might betray a faint shimmer of granularity, not in light, not in matter, but in space-time itself. The GO600 detector in Germany was designed to listen for gravitational waves, the faint ripples of space-time caused by the collision of black holes and neutron stars. Yet some researchers suspected it might hear something else, a restless background hum, not from the heavens, but from the fabric of the universe itself. When unexplained noise did appear in the data, whispers rose that it might be the signature of holographic grain, a first glimpse of the universe's hidden pixels. Though the interpretation remained controversial, the speculation was enough to ignite a wave of experiments. At Fermilab, the holometer was built, an instrument designed specifically to test the holographic principle. Twin interferometers, each splitting beams of laser light, sought to detect jitter at the smallest scales, vibrations not caused by seismic tremors or cosmic waves, but by the finite resolution of space-time. If the universe was a hologram, the holometer would catch its static. The results, when published, found no definitive holographic noise. And yet the pursuit itself revealed something profound, that the question was no longer confined to mathematics. It had become experimental, testable, part of the fabric of empirical science. Reality's deepest secret was no longer beyond reach. LIGO, the great observatory that finally heard the first whispers of gravitational waves, has also become an inadvertent probe of holographic reality. Its unparalleled sensitivity to the stretching and squeezing of space-time allows it to set limits on how smooth the fabric truly is. Though it has not yet uncovered the grain, it has constrained its size, pressing theories into narrower and narrower corridors. Each of these efforts deepens the stakes. For if the holographic principle holds true, then everything seen in the night sky, the galaxies, the stars, even the flow of time, may not be fundamental. They may be projections, illusions rising from the information written on a cosmic boundary far beyond human sight. The cosmic microwave background is no longer just a fossil of the past. It may be a mirror reflecting the code upon which reality is written. Its faint fluctuations may whisper not only of the universe's origin, but of its true nature, a nature hidden in dimensions thinner than perception can grasp. Cosmology, once the study of stars and galaxies, now stretches toward philosophy. The question is no longer simply how the universe began, but what the universe is. If space and time are emergent, then what lies beneath? If everything is projection, what is the projector? The evidence remains incomplete, but the trail of clues is undeniable. The holographic principle, born from the paradox of black holes, has reached into the oldest light in the sky, into the vibrations of laser beams, into the silence of gravitational detectors. Each test does not yet confirm the truth, but each narrows the possibilities, tightening the net around reality's deepest secret. The cosmic background light still glows, silent and patient. It does not answer the question. It only reminds us that the answer is written somewhere, faint but enduring, waiting for human eyes to read it. Beyond the silence of observation and the rigor of equations lies a place where science leans into speculation, a threshold where mathematics whispers possibilities too vast to ignore. Here, the holographic universe becomes not merely an idea, but a mirror held up to reality itself. The principle is deceptively simple. Everything seen in 3 dimensions, stars, planets, the swirls of galaxies, and even the beating rhythm of life, could be projections, shadows cast from information written not in volume, but upon a boundary 2 dimensions thin, a cosmic screen beyond the reach of eyes, carrying the full story of the universe. This vision draws its power from quantum fields, the invisible scaffolding of existence. In holographic models, every particle, every interaction can be re-expressed as data upon a surface. The depth of space is not primary, but emergent. Like the illusion of motion in a sequence of still frames, what is experienced as distance, shape, and geometry could be nothing more than a rearrangement of underlying code. Yet this is not the only vision science entertains. Some physicists suggest that space-time itself is born not from particles, but from relationships, from quantum entanglement, the strange link that binds particles across distance, defying separation, may be the loom upon which space is woven. Entanglement patterns, when dense enough, begin to resemble the curvature of geometry. In this view, the universe is not built upon objects, but upon the invisible threads of connection. Reality becomes a tapestry of relationships, where space and time are consequences, not foundations. Others cast their gaze upon black holes for clues. If black holes store all information upon their horizons, then perhaps the entire cosmos resembles such a structure. A boundless interior enclosed by a boundary where the universe's code resides. Black hole cosmology dares to suggest that everything known, from the birth of galaxies to the rise of consciousness, may be unfolding within the event horizon of a higher dimensional black hole, a universe within a shadow, its depth nothing more than the inside of a cosmic prison whose walls can never be touched. From another corner of theory arises one of the most striking discoveries of modern physics: the AD-S CFT correspondence, proposed by Juan Maldacena in 1997. It revealed that a world with gravity in higher dimensions can be exactly equivalent to a world without gravity in lower dimensions. a duality between spaces that seemed impossible to unite. While the mathematics works most clearly in the geometry of anti-de Sitter space, a universe with constant negative curvature unlike our own, it offers a proof of principle. A confirmation that the holographic idea is not metaphor alone, but exact equivalence. The lingering question remains: could a similar duality hold for our own cosmos, one born not of negative curvature, but of expansion? If so, the universe might be an even deeper hologram than imagined, encoded on a boundary far beyond observation. But science does not move only upon wonder. It also carries the weight of skepticism. For every bold speculation, there are voices of restraint. What if holography is not literal but merely a powerful mathematical tool, a convenient way to translate between languages of physics without demanding that reality itself be flat? Some argue that the principle may reveal deep symmetries but not ontology, that the universe may still be truly three-dimensional, and holography is simply a reflection of the elegance of mathematics. The debate is not yet settled. For every equation that points to projection, another insists upon depth. For every experiment chasing holographic noise, another finds silence. Theories bloom in the fertile ground between proof and uncertainty. Yet what emerges from this dialogue is more than speculation. It is a profound reimagining of reality. If space and time are emergent, then they are not eternal absolutes, but fragile constructs. If the universe is holographic, then existence itself is a story written upon a page we cannot see. If the cosmos is the inside of a higher dimensional black hole, then the boundaries of reality are far stranger than imagination dares. To ask whether the holographic principle is true is to ask what it means for reality to exist. Is existence a stage of depth and substance, or is it the play of shadows upon a screen? In the quiet corridors of theoretical physics, these questions linger like echoes in an endless hall. Speculation is not the end of science. It is the light cast ahead into the unknown. The shadows it creates may not be truth, but they guide the way toward it. And in those shadows, the possibility remains that everything, every galaxy and every thought is written upon a surface thinner than a whisper. The universe may not be what it seems. It may be less, and in being less, it may be infinitely more. In the quiet halls of physics, theory alone is not enough. The equations may suggest that the universe is holographic, that space itself may be woven from information, but without observation, the vision remains only a shadow on the wall. To move closer to truth, humanity builds instruments, machines of staggering delicacy and ambition, designed to listen for whispers in the fabric of existence. The search begins with gravitational waves, those faint tremors of spacetime born from the collisions of black holes and neutron stars. At observatories like LIGO in the United States and Virgo in Italy, beams of laser light are split and stretched across vast corridors of vacuum. They are tuned to detect distortions smaller than the width of a proton, the cosmic echoes of cataclysmic mergers light years away. Yet hidden in their sensitivity lies another possibility, the chance to glimpse the quantum jitter of space-time itself. If reality is pixelated, written in Planck-sized units, then the detectors may capture its static, a restless shimmer not from the cosmos, but from the very stage upon which the cosmos unfolds. The idea of holographic noise lingers at the edges of their data. Unexplained. Patterns, subtle and faint, raise the question, are these disturbances artifacts of the instruments or the trembling of reality at its foundations? Though no conclusive signal has yet emerged, each refinement of sensitivity brings science closer to an answer. Each run a deeper gaze into the fabric that holds all things. At Fermilab, a bold attempt was made to confront this mystery directly. The holometer experiment, built in 2010, used twin interferometers set side by side, designed to catch the telltale jitter of space-time grain. Laser beams were split and recombined, their interference patterns watched for a correlated flicker, a whisper of the Planck scale. The results were inconclusive, finding no definite holographic signature, but the very attempt marked a new frontier. The recognition that questions once confined to philosophy could be tested in the laboratory beyond Earth. New eyes now open upon the heavens. The James Webb Space Telescope, with its vast golden mirrors, peers deeper into time than any instrument before it. Its gaze reveals galaxies forming in the first few 100 million years, patterns of structure that may one day hint at the laws beneath the holographic code. If spacetime itself is emergent, then the earliest epochs of the universe may carry its fingerprints. Webb is not built to prove holography, but its precision offers data of such richness that even theories of projection may find guidance in its revelations on the ground. Other giants push at different boundaries. The Large Hadron Collider at CERN smashes protons together at energies once reserved for the birth of the universe itself. Its collisions may hint at strings vibrating in hidden dimensions, or new particles, that betray the architecture of spacetime. Though no direct proof of holography has yet appeared, each constraint it delivers sharpens the contours of what is possible. And in its magnetic fields and crashing beams, humanity rehearses the symphony of creation, seeking the hidden score behind the performance in another realm altogether. Quantum computers and entanglement studies begin to illuminate the possibility that space itself arises from information. By weaving qubits into intricate networks, researchers find echoes of geometry emerging from patterns of entanglement. It is here, in the dance of correlations, that the dream of emergent spacetime finds its most vivid laboratory. Theorists suspect that if the universe is truly holographic, then entanglement is its fundamental currency and computation its hidden language. Yet for all these efforts, the challenge remains immense. The Planck scale, where the grain of spacetime would reveal itself, is far beyond the reach of current instruments. It is a realm so small, so finely hidden, that probing it directly is like trying to read the ridges of a fingerprint from across the breadth of a continent. Each experiment edges closer, but the horizon of certainty retreats just as quickly. Still, science advances. Each attempt, whether at LIGO, Fermilab, CERN, or through the distant gaze of Webb, tightens the net. Each refinement narrows the shadows, demanding more of the theories that dare to describe the universe as two-dimensional. The pursuit itself becomes part of the story, a testament to humanity's refusal to rest content with surface appearances. For even if the tools cannot yet touch the Planck scale, they reveal something deeper: the willingness to imagine beyond sight and to build instruments delicate enough to listen for whispers in the silence. The search for holographic noise, for emergent geometry, for the signatures of hidden dimensions, is not merely a scientific endeavor, it is a philosophical act, a declaration that truth, no matter how thinly veiled, may one day be revealed in the beams of light that race through interferometers, in the golden mirrors that unfold in the vacuum of space. In the collisions that ignite beneath the soil of Europe, and in the fragile entanglement of qubits across circuits of silicon, the same question is asked again and again: is reality as it appears? Or is it only a projection, a shadow written upon a boundary that can never be reached? The answers have not yet come, but the tools are waiting, listening, searching. And in their silence, the mystery deepens. If the universe is only two-dimensional at its foundation, then all of existence is suspended upon a paradox: the galaxies stretching across billions of light years, the stars burning in silence, the fragile arc of memory within a human mind, all may be shadows, projections rising from a surface beyond reach. The solidity of matter, the flow of time, the intimacy of experience may not be fundamental, but illusions cast by information etched upon a boundary unseen. This vision unsettles the roots of perception. For what does it mean if depth is not real? If the very stage of reality is only appearance? To think of the universe as holographic is to suggest that life itself may be woven from echoes, that what is touched, remembered, or longed for may be written elsewhere, on a flat horizon, where every particle and every thought is no more than code. Philosophers of the ancient world once hinted at such shadows. Plato spoke of a cave where prisoners watched flickering shapes upon a wall, mistaking the phantoms for truth. In his parable, reality was hidden beyond the cave's opening, waiting for those who dared to turn their eyes toward the light. Modern physics now returns, unexpectedly, to that same imagery. Perhaps the cosmos itself is a cave, its depth an illusion, its truth painted upon the boundary that contains it. And yet, even if this is so, the shadows remain no less meaningful. For the prisoner's dream is still his world, the echo still carries memory, the illusion still births love, grief, and wonder. Illusory or not, experience remains real to those who live it. The hologram does not lessen life. It only reframes it as part of a mystery grander than the eye can contain. In the mathematics of projection, time may be no more than a coordinate, a dimension emerging from information flow. If so, memory is not a fixed recording, but the unfolding of code. The past is no longer behind, nor the future ahead, but all inscribed upon the surface of reality, waiting to be revealed in sequence. Such a vision collapses the familiar, but it does not destroy meaning. It only invites the thought that meaning itself may lie deeper than dimension, beyond geometry, rooted in the act of existence. If the universe is a projection, then questions sharpen into sharper paradoxes. What is the projector? Where is the screen? What lies beyond the surface upon which the cosmos is written? Science cannot yet answer, for to cross beyond the boundary is impossible. It is not a place, but a principle, a limit that frames all things, but cannot be. Stepped across in this silence, reflection turns inward. Perhaps the true significance of holography is not that the universe is less than it appears, but that human beings are capable of asking. In the shadows of Plato's cave, in the holograms of physics, in the endless data of experiments, the same impulse arises, the desire to understand this longing, immeasurable and unquantifiable, may itself be the one dimension that cannot be reduced. The dimension of wonder. It is here that science and philosophy converge, for whether reality is three-dimensional, two-dimensional, or something stranger still, the act of questioning reveals something profound. The universe may be projection, but the search for truth is not. The journey to know is not illusion, but the most authentic thread in the tapestry of existence. When the detectors fall silent, when the equations end in paradox, the mystery remains. And in that mystery lies the essence of being. Perhaps the universe is a surface, a code, a hologram, but the human quest to see beyond, to imagine more, to stretch mind across the abyss of the unknown. That is a depth no projection can flatten. The stars may be shadows, the galaxies illusions, time itself a mirage. But the wonder they awaken is real, and in that wonder the universe finds its truest dimension, not written on a boundary of space, but etched within consciousness, unbounded, infinite, and profound. In the end, the universe remains an unanswered riddle. A canvas that may be painted with shadows instead of substance. A grand design where depth may be no more than an echo upon a distant wall, if reality is a projection. Then every galaxy, every star, and every heartbeat is a glimmer of information, written on a horizon we cannot touch. Perhaps we are no more than whispers, etched into the fabric of something greater, and perhaps that truth does not diminish us, but makes our story infinite. From Plato's cave to modern physics, the question has never been only about matter or time or light. It has been about meaning, about wonder, about the will of human beings to look upward into the darkness and ask why there is something rather than nothing. And so the search continues, not for answers carved in stone, but for the endless horizon of mystery itself, a horizon where science, philosophy, and imagination converge. For in that pursuit, in the fire of curiosity that no paradox can extinguish, lies the most real dimension of all the depth of wonder that defines what it means to exist.